Before we get started, I want to give you a heads up. This talk is a little longer than I intended it to be. There was just so much content I want to stuff into it. But fortunately, I consulted with Kevin and with Patrick last night, and I think we'll be able to get you out of here in time for your break. So with that out of the way, hi, I'm Lynn Clark, and I make code cartoons. I also work at Mozilla in the Emerging Technologies group. So that's things like the Rust programming language, and Servo, which is a super fast browser engine, and WebAssembly, which I'll be talking about today. If you look at the schedule, this is the official title of the talk. This is the title that the organizers and I came up with a few months ago when we were talking about this. But as I started preparing for this talk, I felt like I really wanted to amend this. Now, I thought of changing it to this, what WebAssembly could potentially mean for React. But instead, I decided to go with this one. And I really like this one because it's reminiscent of a whiteboard, and that really reflects the kind of talk I'm going to be giving today. I'm going to be sketching out some ideas for what WebAssembly could mean in React. But these are just a few of many ideas. So what the future of WebAssembly is in React could be very different from the picture I'm painting here. I've been lucky. I've been able to discuss many of these ideas with lots of different people, both inside and outside of the React community. And in particular, it was my conversations with two people that really informed the content of this talk. Those two people are Luke Wagner, who was one of the folks who came up with Asm.js, a precursor to WebAssembly. And he also did a lot of the work pushing WebAssembly forward. And Sebastian Markbitch, who of course is on the React core team and has been very involved in the Fiber work around the new reconciler. So this talk doesn't just reflect my own insights, but it also reflects the insights of a number of other people. Now I'm going to start the talk by looking at how WebAssembly could be incorporated into React in a pretty straightforward way today. And then I'll explore what the impact of that could be. After that, I'll look at the future. I'll look at what changes are coming in WebAssembly and what changes the React ecosystem might see and what tooling might come about, and how those could all come together to create new possibilities. Before I go into any of that, though, I'm going to explain a little bit about what WebAssembly is. Now, I just gave a whole talk about this at JSConf EU 2 weeks ago, so if you really want to know in detail, I'd recommend watching that talk. But to summarize, up until this point, if you were developing a web page and you wanted to run code, so you wanted to do something like change the DOM in the response to an event, or run a calculation, you had to use JavaScript to do it. Now with WebAssembly, you'll be able to use other languages to do those things too. This presents a couple of possible benefits to React. One of these is code reuse. So you could rewrite something like the reconciliation algorithm in a language like C, which on React Native could then compile down to native code. Another possible benefit is that it could make React applications run faster in the browser. WebAssembly can, under some circumstances, run faster than JavaScript. So those are the potential benefits. Now let's look at the different parts of a React application and see which parts we may be able to convert to WebAssembly today. The different parts are the core reconciler, which looks at the previous version of an app and the next version and figures out where the changes have been. And then the renderer takes those changes and pushes them out to the UI. There's also some additional code, like the event delegation system. And then, of course, there's your code, the application code, so things like components. At the moment, there are parts of this code that are going to be easier to convert to WebAssembly than other parts of the code. And that's because the WebAssembly that's in browsers, the WebAssembly that is shipped on by default in Firefox and Chrome in March and is currently in preview versions of Edge and Safari, is just the MVP, the minimum viable product. It doesn't yet have all of the features that we expect to have in WebAssembly. One of the features that's still missing from WebAssembly is direct access to the DOM. And that means that you can't call DOM methods directly or interact with JavaScript objects at the moment. And I'll explain more about what that means later. But because of this, it's going to be harder to code things like the renderers or the event system in WebAssembly, at the moment at least. Another option would be for developers to do their components in WebAssembly. But in order for that to work, developers would have to be writing in languages that compile to WebAssembly. And right now, that's things like C and C++. React application developers probably don't want to be coding in C. So at the moment, this isn't a great candidate either. That leaves the reconciler. And this is actually a good place to start. Like I mentioned before, there's potential code reuse with the reconciler. So let's walk through and see what the system would look like if we did this, if we wrote the reconciler in something that compiles to WebAssembly. When the user loads the page, it would load in the same way. They would download React.js, because you still need JS in order to boot WebAssembly modules. And in addition, a WASM file would be downloaded. So that contains the WebAssembly code. That's just a binary. And we'll need to load this code in order to run it. So first comes the JavaScript, which loads the JS part of React. And React will then create an instance of a WebAssembly module, the reconciler. To do that, it will use WebAssembly.instantiate. Let's take a closer look at what this function does. The first thing we pass in is going to be the binary code that we got in that WASM file. That's the module code. So we extract the binary into a buffer and then pass it in. The engine will start compiling it down to something that's specific to the machine that this browser is running on. Now, if it were JavaScript, loading this module would make the main thread busy. I've talked about this before, about how the main thread is like a full stack developer. It's in charge of things like layout, JavaScript, the DOM. One of the other things that it helps out with in JavaScript is compilation. If we were instantiating this JavaScript module here, the main thread would be right here with us. And that means that it can't be getting to its other tasks like layout or running other JavaScript. Now, this isn't a huge problem with Fiber, because Fiber can initialize JS code lazily, but it's still going to take up some time on the main thread. One of the neat things about WebAssembly is that it doesn't need to take up the main thread's time to do this compilation. It can actually do this compilation off of the main thread. So that what WebAssembly instantiate is going to return is a promise, because that lets the main thread get back to its other work. Then, once it's finished compiling the module, the compiler will use the promise to let the main thread know that it has this instance for it. But the compiled module is not the only part of the instance. I think of the module as kind of like an instruction book. And the instance is like a person who's trying to build something using those instructions. But in order to make something, they need some raw materials that they can work with. This is where the second parameter to WebAssembly instantiate comes in. And that is the imports object. I think of the imports object kind of like a box of these raw materials that the instance is going to use to build the thing with those instructions. That imports object can have 4 different kinds of imports. It can have values, which are basically global variables, and they're restricted to WebAssembly types. At the moment, that means things like numbers, so integers and floats, but that will expand over time. It can also have function closures. So this means that you can pass JavaScript functions in, which WebAssembly can then call. Now this is useful because, as I said before, you can't directly manipulate the DOM with WebAssembly. So what you can do is set up a JavaScript function that can manipulate the DOM in the way that you need, and then call that from WebAssembly. Another kind of import is memory. And this concept of a memory object, it confuses a lot of people. So I want to go a little bit more in depth on this one. First, I'm going to give you a little crash course in how memory is managed in different programming languages. And then I'm going to explain why we have this memory object for WebAssembly modules. You can think of memory in a machine as a bunch of boxes. I think of this kind of like the mailboxes that you have in an office, or like the cubbies that you had in preschool where you could put your stuff during the day. If you need to leave something for one of the other kids, you could just put it in one of these boxes. And next to each one of these boxes, there's a number. That is how you could tell somebody where they could go find the thing that you left for them. And in memory, these are called memory addresses. Each one of these boxes is the same size. It can contain the same amount of info. And the size of the box is specific to the machine. It's called the word size. Now, it's usually something like 32 bits or 64 bits, but I'm going to use a word size of 8 bits just so it's easier to show you things. If we wanted to put a number like the number 2 into one of these boxes, we could do it pretty easily because numbers are really easy to represent in binary. But what if we want to represent something that's more complicated than a number? Something like the letter H. We would need to have a way to represent it as a number. And to do that, we need an encoding, like UTF-8. And then we need something to actually encode the letter into the number, like an encoder ring. Once we get it turn it into a number, then we can store it really easily. Now when we want to get it back out and turn it back into an H, we have to go through a decoder to get back to that H. When you're working in JavaScript, you don't actually need to know about this. This memory management is abstracted away from you. It means that you don't need to touch the memory directly. Instead, the JS engine acts as an intermediary. It manages the memory for you. So let's say some JS code like React wants to create a variable. What the JS engine does is run the value through an encoder, and then it gets the binary representation of the value, and then it finds space in the memory where it can put that binary value. This process is called allocating memory. Then the engine will keep track of whether or not this variable is still accessible from anywhere in the code. And when it's no longer accessible from anywhere in the code, it will reclaim that space so that it can put other values there. This process of washing the variables and clearing it out when the variable can no longer be reached is called garbage collection. Languages like JavaScript, where the code doesn't deal with memory directly, are called memory-managed languages. And this automatic memory management can be very helpful for us as developers, but it also adds overhead. And that overhead can make your performance unpredictable. Now, WebAssembly is different. It doesn't offer that layer of abstraction. Instead, you're operating directly on the memory. WebAssembly only gives you two memory operations. You can load and you can store. And when you're doing one of these, you're working on a single memory address at a time. If you're writing a higher level language like C or C++ and then using a tool to compile it down to WebAssembly, the tool that you use will probably add some code that helps with this, that does some of the things that the JS engine does for you. Like it might ship down some code for encoding and decoding these bytes. Sometimes these tools add even more helpers and APIs, language-specific ones, to make it simpler for you to interact with WebAssembly. That code is called a runtime environment. So that's memory management in a nutshell. Now let's look at how the memory import is created and why it's created. I'm going to tip these mailboxes on the side so that I can show WebAssembly and JavaScript working together. Now React is going to create a memory to pass in as an import. All the JS engine is going to do internally is create an array buffer. That's just a JavaScript object, so JS has a reference to it. And JS allocates the memory for you. You tell it how much memory you need, and it will create the array buffer of that size. And if you need more memory later, you can ask it to grow that memory. Handling WebAssembly's memory as a JavaScript object, as this array buffer, does a few things for us. Because it is just a JavaScript object, that means that JavaScript can also dig around in the bytes. So WebAssembly and JavaScript can both be digging around in these bytes. And in this way, they can share memory and pass values back and forth through that memory. Instead of using memory addresses, they use array indexes to access each of these boxes. For example, the WebAssembly could just put a string in memory. It would encode that, encode it into bytes, and then put those bytes into the array. And then it would return the index, the first index, which is an integer, to JavaScript. So JavaScript can pull the bytes out and use them. Now, most JavaScript doesn't know how to work directly with bytes. So you'll need something on the JavaScript side, like we have on the WebAssembly side, that can convert those bytes into something more useful, like a string. In some browsers, you can use the text decoder and encoder APIs for this, or a tool like Emscripten can add some functions to your JavaScript that help with this. So that's the first benefit of WebAssembly memory just being a JavaScript object. The WebAssembly and JavaScript can pass values back and forth to each other pretty easily. A second benefit of this WebAssembly memory just being a JavaScript object is that it prevents memory leaks. When the WebAssembly instance that this memory is attached to goes out of scope, this whole memory array can just be garbage collected. Finally, and most importantly, it provides memory isolation. The bounds of the array provide a boundary, a limit to the memory that the WebAssembly module can touch directly. It can directly touch any of the bytes that are inside of this array, but it can't see anything that's outside of the bounds of this array. For example, any other JavaScript objects like the window global aren't accessible to it. It can't dig into those bytes. Now, when people hear that WebAssembly gives you direct access to memory, they get concerned because they think that a WebAssembly module would have this direct access to other parts of memory. But whenever there's a load or a store in WebAssembly, the engine does an array bounds check to make sure that you're staying within those bounds. And if the code tries to access a memory address that's outside of those bounds, the engine will throw an exception. So that will protect the memory outside of this memory object. So that's the memory import. The final type of import is related to security as well. It's called a table. Sometimes in a program, you want to be able to have a variable that points to a function. Something like a callback that you can pass around and pass into other functions. In C, these are called function pointers. The function lives in memory, and the variable, the function pointer, just points to that memory address. And if you need to later, you can point it to a different function. So this should be a familiar concept. In web pages, all functions are just JavaScript objects, which means that they live outside of WebAssembly's memory. If we want to have a variable that points to one of these functions, we need to take its address, which is this number, and put it into our memory. But part of keeping web pages secure is keeping those memory addresses hidden. You don't want code on the page to be able to see or manipulate that memory address, because if there's malicious code on the page, it can use that knowledge of where things are laid out in memory to create an exploit. For example, it could change the memory address that we've stored here to point to a different memory location. And when you try to call the function, instead of calling what you wanted to call, it would load whatever is in the memory address that the attacker gave you, which could be malicious code that the attacker got in there somehow, like embedding it in a string. Tables make it possible for you to have function pointers, but in a way that's not vulnerable to this kind of attack. A table is an array that lives outside of WebAssembly's memory. So it's outside of the memory that WebAssembly can look at directly. The values are references to functions, so internally these references contain memory addresses. But because it's not in WebAssembly's memory, WebAssembly can't actually see that memory address. But it can see the indices. If the WebAssembly module wants to call one of these functions, it passes that index to an operation called callInDirect, which will call the function indirectly. Right now, the use cases for tables are pretty limited. They were added to the spec specifically to support these function pointers, which are pretty important in C and C++. And because of this, the only kinds of references that you can store in them are functions. But as we get things like direct DOM access, you're probably going to see more different kinds of references being stored in these tables. So these are the different kinds of imports that you can equip your instance with. You can have values, function imports, memory, and tables. And your instance is now fully equipped and ready to go. It has this instruction manual, which is the compiled code, and it also has all of its imports. Now, the promise that we got when we called WebAssembly.instantiate can be resolved. We have the instance of this WebAssembly module, which means that we can start rendering with it. To kick off the rendering process, you'd still do what you do today. Your code would call react-dom.render, and it would pass in an element and a DOM node, which would serve as the container. Now, these are JavaScript objects, so they live outside of WebAssembly's memory. React-dom.render is still a JavaScript function, but inside of this JavaScript function, it's going to pass off control to WebAssembly, which is going to build out the fiber tree. And if you want to know more about how the fiber tree is built out, I gave a whole talk about that earlier this year at ReactConf. We need to create an instance for this element. But because these two objects live in JavaScript's memory, WebAssembly doesn't have direct access to them for now. So we need a way to call functions on them. And this is where those function imports come in. We'll have equipped our instance with a function that can actually do this for us on the JavaScript side. So we would have a function import that knows how to create a React instance from an element. And this function import, as part of its closure, would have an array of elements. And we would have put the first element into that. And there would also be an array for holding on to the instances. Now, to actually create the instance for this first element, the WebAssembly module would call the JavaScript function. The function would create the instance and put it in that array of instances. Then we'll return the index, that integer, that is the index of this instance. So let's jump ahead a little bit to where we're calling render on that instance. What WebAssembly would do is pass that index into another function import. And that would call render on the instance and create the elements, and then add those elements to the elements array. And then it would return an array of indexes for the elements. That's actually a pointer to an array, but that's not too important. As this WebAssembly module goes along building out these instances, it's also going to be building out the corresponding fibers. But it's going to be putting those in its own memory. The fiber data structure was actually designed so that it could be used in something like WebAssembly. It could be used from a language like C. There's a fixed set of fields on it, and those fields are predictable in their size, so it's really easy to allocate them. And most of these fields are easy to represent in WebAssembly's memory. There are references to other fibers like child, sibling, and return, so those are just addresses, which are easy to represent as numbers. Or they are enumerables, which means that they can be represented as numbers. For those fields which do need to point to JavaScript objects, we can just use the array indices that we've been getting back from these function imports. So the WebAssembly module will build out this whole fiber tree in this way, and then it will return control back to JavaScript, which would make the changes to the DOM. So, what exactly does this do for React? As we talked about before, it can help with the reuse of code. Because it's written in C, we could share it with React Native, where it could easily compile down to native code. But will it help with the performance of React applications in the browser? The truth is, the short-term immediate impact of this on performance isn't clear. So let's break it down and see why. Here's a diagram that shows the kind of work that the JS engine would typically do for a JavaScript app. For each category, let's look at the potential for performance improvement here. Decoding WebAssembly is faster than parsing JavaScript, which could potentially help. But we're not actually rewriting a whole lot of the code base here, so that's not going to be huge. Compiling and optimizing WebAssembly is also faster than JavaScript. But again, since most of the code will still be JavaScript, we won't see as large an improvement here as we would otherwise. Re-optimizing is something that the JS engine has to do sometimes. But in an application or framework like React, there's actually not that much re-optimization happening. Because as Dominic talked about earlier this morning, there are a lot of performance-focused devs working on React who know the tricks of the JavaScript engine internals. And then there's execution of the code. WebAssembly instructions can execute anywhere between 10% and 800% faster than the equivalent JavaScript. But the operations in React are likely to be on the lower end of that spectrum, not the higher end. Finally, there's garbage collection. There probably will be some savings in garbage collection, but not as much as you'd think. And that's because a lot of the garbage that's created in React is elements. Each time you go on a pass-through render, you have to create a new set of elements. And for now, those elements live in JavaScript. Unless we can move things like those elements to WebAssembly's memory, there won't be much savings here. You may be wondering why I said it's a question of whether or not WebAssembly would make React faster, because I've said that in all of these areas, it could make it at least a little bit faster. The reason it's a question is because doing what I've described introduces a little bit of overhead. First off, we're adding a little bit of code to the two files that we wouldn't have to add if we were just working with JavaScript. So for the example, the code we need for encoding and decoding bytes in JavaScript, and the same code that we need in WebAssembly. And the additional code would also include that runtime environment. Now, a lot of people get confused. They think that you have to have a huge runtime environment to do stuff in WebAssembly, and that's not actually true. You can pare down your runtime environment to just the functions that you need based on what code you're doing. But we still probably will need some runtime environment, a little bit at least. Additionally, there's a little bit of a cost for these calls from JavaScript to WebAssembly and from WebAssembly to JavaScript. This is just an issue for the time being. There's nothing inherent to calling WebAssembly from JavaScript that makes it slow. It's just that in the browsers, in the current JavaScript engines, this hasn't been optimized. So for example, in Firefox right now, if you're making a call from JavaScript to WebAssembly, it has to go through a setup function. And this slows things down slightly when you're first making that call. We're only talking nanoseconds here, but if you're calling between these two a lot, those nanoseconds will add up. Now, when you're calling the other way, when you're calling from WebAssembly to JavaScript, Firefox is actually pretty fast. But it's not as fast as it could be. It's not as fast as JavaScript to JavaScript calls can be if they're fully optimized. So right now, if you have a lot of communication between JavaScript and WebAssembly, this overhead can add up. But as engines optimize this away and bring these function calls up to speed, this overhead will be less and less. With all of this in mind, the short-term performance impact of doing what I've suggested, of rewriting the reconciler in a language that compiles to WebAssembly, is probably either a wash or a modest improvement. So that's in the short term, like the next 3 to 6 months. But if you think a little bit longer term, if you think about what it could mean in a year or two from now, that's a different story. So everything I'm going to talk about from here on out isn't stuff that's in the browsers today or tooling that we currently have in React, but instead is stuff that's on the roadmap for WebAssembly or is tooling that we could potentially build. One of the things that was slow in the approach that I just described was interacting with instances and elements, which are JavaScript objects. Now, part of that cost will go away once browsers improve, but even with that, there are some performance opportunities we just can't tap as long as the instances are in JavaScript. For example, they live in JavaScript's memory. So JavaScript has to spend time keeping track of them and garbage collecting them. That cost is going to be there unless we can move these to WebAssembly's memory. And that means that we'd have to have that component code in WebAssembly. But we already said that we don't want component authors to have to write in a language that compiles to WebAssembly. I asserted that before, and I think that a lot of you probably agree with that. I want to take a step back, though, and I want to look at the assumptions behind that assertion. One of the assumptions there is that JavaScript is easier to code, and in a lot of ways it actually is easier. It's easier to get up and started with JavaScript because you don't need to learn about types or how to use a compiler. The early part of the learning curve for a language that can compile easily to WebAssembly, something like Rust, probably looks something like this, whereas the same part of the learning curve for JavaScript looks more like this. But as the performance requirements for your project increase, I'd say that the learning curves start looking more like this. And that's because it's actually kind of hard to optimize JavaScript. You have to know a lot about JavaScript engine internals. So it would be nice if we could have the advantages of JavaScript. If we could have the speed of prototyping that you have with JavaScript, but also have the predictable performance of something like Rust when we're actually running the code. So I want to throw a what if out there. What if we could write some of the components in JavaScript and have other ones in WebAssembly and run them side by side? Now, making languages interoperate in this way is a known hard problem, so I do not want to imply otherwise. But with the way that boundaries are set up in React, and with the way that components are decoupled from each other, it may actually be possible. This could open up some really interesting workflows. For example, you could prototype a whole bunch of components in JavaScript and then profile to see where your pain points are. Then you could just do those ones in WebAssembly. Other people have ideas for how you could make tooling that would make this much easier. And if the tooling made it easy enough to write some or most or all of your components in WebAssembly, then we could see savings from parse and compile. And we could see savings in garbage collection. But even without that tooling, if React makes it possible to have some of your components written in WebAssembly, then we could get rid of a lot of that re-optimization for components that are hard to optimize in JavaScript if you aren't a performance expert. So that's one place where changes in React itself and changes in tooling could open up new possibilities. There are also additions coming in WebAssembly that could lead to some big wins. The first of these is support for threading. That will open up the possibility of parallelizing the reconciliation algorithm. Running work in parallel can make things faster, and that may seem like a pretty self-evident statement. But running things in parallel doesn't always make it faster. And in fact, the React core team actually did some experiments using the tools that were around about a year ago to see how it would work, and they found that parallelizing the work would actually make things slower in a number of use cases. They were using web workers in JavaScript, and there were a couple of reasons why this isn't as fast as you'd expect it to be. First off, the memory between different workers is isolated, or at least it was at the time. If you need to share data between these workers, then you need to actually send a message that will copy the data over to the other memory. It would be a lot faster if the memory between these workers was shared, if you could both act on the same memory at the same time. Now, since the React team did this experiment, shared array buffers, which provide this kind of functionality, have become more of a reality. So if they were doing this experiment today with the tools that are available today, they might see some different results. But shared array buffers don't make it possible to share JS objects, which are easy to operate on. Instead, you're just working with bytes, just like you are with WebAssembly's memory. And multiple workers can be touching those bytes at the same time, which means that you can have race conditions. This makes working with shared array buffers kind of tricky. You really want to have nice abstractions on top of this. And there are some abstractions that have been added to JavaScript to help deal with this. But really, this kind of shared memory concurrency is very new to JavaScript. With WebAssembly, you could choose a language like Rust that has a focus on concurrency and gives you the right tools for the job. Shared array buffer helps with the cost of sharing data between web workers. Another cost in parallelizing is sharing code between these web workers. As I mentioned before, JS objects aren't shareable between web workers. And of course, the code that you're using, things like your components and React itself, are just objects. This means that even though you've loaded the code in one web worker, it's not there in the other worker. You're still going to need to load it again in the other web worker, which includes that compilation and optimization and re-optimization step each time. But in WebAssembly, you actually have the compiled module. Remember, the compiled module is like an instruction book. When WebAssembly instantiate returns that promise with the instance, it also returns the module itself, which makes it really easy to spin up new instances. So that makes it really quick. The support for threads that enable this kind of parallelization in WebAssembly is getting very close. Another thing that's going to come to WebAssembly pretty soon is direct access to the DOM. I was talking about this before. That's why we needed these function imports in order to manipulate the DOM. With WebAssembly, we don't currently have a way to call methods directly on the DOM. But once you have direct access to the DOM from WebAssembly, these functions won't be needed anymore. And at that point, there are fewer barriers to converting all of React, including things like the event system, to WebAssembly. Another thing that's on the horizon is integration with the browser's GC, the built-in GC. Right now, if you want to run a garbage collected language, you can ship down your own GC as part of the WASM file. This will run side by side with the browser's GC, but that's not easy to do right for a number of different reasons. Once you have integration with the browser's built-in GC, then WebAssembly compiled languages will just be able to use that. So this could mean big things for languages like Elm or possibly even OCaml and Reason. Unfortunately, that's about all I have time to cover in the talk today. But I want to be clear that these are just a few of the ideas that people are talking about. People are also talking about ideas like incorporating a bytecode interpreter, kind of like what you would see in Glimmer. And of course, ideas like that would completely change the way that WebAssembly works in React. So I can't tell you what WebAssembly means for React precisely, but I hope this talk has given you an idea of what it could. Thank you again to everyone who talked through these ideas with me, especially to Sebastian and Luke. And thank you all for listening.